Trying to record. Just trying to record stuff. Oh my. There we are. There we aren't. There we are. Okay. I'm going to share my screen. I'm such a sharing person. Okay. Can everybody see? Okay. Here it is. So I kind of asked this. RJ said maybe it was a fail because it was really hard to understand. This is, these are two lines. They are coincident lines, meaning that they are basically the same line. But they're defined with two different vectors. Or sorry, two different position vectors and two different direction vectors. Over here, I'm changing the scalar that I multiply the vector by sliding it. Okay, and you can see that. Actually, it looks like it passes through point 2. This one I've got the traces on. You can see that it traces out a line. And actually, why don't I just? So I'll show you what it looks like. Ah. There you go. This isn't quite such a fail as my parallelopipe so far. Okay, down to 0. I'm going to move it again. Get rid of the traces. And I'm going to trace both of these. I'm going to trace that one. And what you are going to see is that the line that's made by that is the same as the line that's made by that vector equation of the line. So that combination of position and direction vectors all make the same line. Okay, so we have a special thing going on here. Right? So if you look all around, in 3 space, yes, we can see that makes the same line. Does that make sense, RJ? You see they all make the same line? Meg, you see they all make the same line? She refuses to answer. You know what it is? We can't hear her. Can you turn on your speaker? RJ's going to bring you up on the speaker. Meg, don't worry.
I think the speakers died.
Yeah, my speakers are acting funny. Okay, RJ's speaker's not going to work.
It just echoes. Could it be like a function of one maybe?
I don't know what it would be. Hey, can you talk? Is she talking and no sounds coming out?
Yeah, she just talked.
Okay.
I can see the green bar.
All right.
Type.
Type now.
Or speak or something.
Is she talking?
Yep. So
Okay. Still not working. Oh, darn it all. Okay. Great. I know what.
Is that hook up your Bluetooth?
I don't have Bluetooth on this.
And it didn't come with the cable?
Hey, you know what, Meg? We're going to do this so that RJ has to answer all the questions. RJ.
It's not be that way.
Oh, RJ's going to put on his headphones? Is that so that you can listen to Megan?
That way, if I have to hear that, I can.
Okay, so Megan, you are channeling through RJ. RJ's going to be able to hear you. It's just, I won't be, so we can pretend like I'm a deaf teacher.
This is not going to work.
No?
I'm hearing you like twice.
Okay.
And myself.
Because RJ is hearing the goodness of Mr. Rogers twice, he doesn't want to do this.
It's confusing since there's like a 2 or 3 second delay.
Okay. So I guess here's my question for you to answer for all of us, RJ. What has to be true about the two direction vectors for this system to make the exact same line?
They have to be positive.
They have to be positive? No. Have to be positive?
They have to equal each other.
They have to be equal. The direction vectors have to be, and by equal, do you mean equal length?
Or do they have to be equal magnitude?
That magnitude and length are the same thing.
Not magnitude, direction.
They have to be in the same direction, right? Because if our two direction vectors are in different directions, then our two lines are going to head off in two different directions, right? So I don't know if I can do this, but if I move that direction vector now, the lines aren't going to be the same, right? So the direction vectors have to be scalar multiples of each other. Okay. So, we have.
You still get to stop screen sharing.
I have to stop screen sharing. Thanks, Meg.
She didn't say anything.
She's so patient.
Maybe you could say anything.
Oh, I just heard her.
There it's gone.
Okay.
I think so.
My deafness was overcome for just a minute. So fundamentally, for lines to be coincident, the direction vectors have to be what we call a scalar multiple of each other. Okay, so for example, the first direction vector has to be maybe 2 times the second direction vector. It doesn't really matter when we're multiplying by a scalar multiple, it just changes the length. But as long as they are in the same direction as each other, we're going to have 2 coincident lines. Okay, I'm screen sharing again, and I can hear Megan. I can now hear you.
Okay, sweet.
Yeah.
Can you hear me now?
Can you hear me now? Yep, I can hear you now. I think it's on and off, and I think it, yeah. So we'll do our best. The important thing is that the teacher is the one that's being heard.
I'm very much questioning now if I hit that arrow on the profile and hit ignore, if it'll give you just for me or everyone. That's my question.
Oh. RJ's wondering about ignoring me.
It stops back up.
Okay, what do you notice about point 1 and point 2? What has to be true about point 1 and point 2? Oh, Meg Thompson joined.
And now she's joking.
Why am I doing this?
You might as well join as many times as you can. We can hear you now. What do you notice about P1 and P2 in this magical concoction of...
Are they the same distance from each other? No, they're not.
Nope.
They're on the coincident line.
They're on the coincident line, yeah. Do you notice something about P1 and P2 relative to the direction vectors? Take a look at your screen.
Oh.
You notice something about P1 and P2 relative to the direction vectors?
Parallel.
They're parallel, right? Yeah. So the vector between those two. Oh, I think I brought it up. Yeah. No, I didn't.
I find that interesting. there's an echo for you, but when you're Megan, it's the same time as the speakers.
Okay, there we go. Yes, so in fact, if we drew a vector from P1 to P2, we'd see that that vector has to be the same, it has to be a scalar multiple of one of the direction vectors. So really what we're saying is vector OP2 minus vector OP1 is the scalar multiple of one of the direction vectors. So these two conditions have to be true.
T1 is equal to the direction of 2 minus the direction of 11.
Sorry, what was that, RJ?
T1 could be equal to the vector OP2 minus OP1.
Exactly, right? So really what we're saying is OP2, the vector that's going from point 1 to point 2, or OP2 minus OP1, has to be a scalar multiple of D2. Okay? And D1 is also a scalar multiple of D2. So if we know those two lines are equal, this is a little problem we're going to examine. We want to prove that OP2 minus OP1 is a scalar multiple of the second direction vector, for lack of a better argument. And we also want to prove that D1 is a scalar multiple of D2. Okay? Does that make sense so far? So if OP1 is on line 1, and line 1 is the same as line 2, then OP1 could be expressed as OP2 plus some scalar multiple of D2. So in other words, I can get to this point OP1, since it's on the line, by starting at OP2 at that point, and, oops, I should have my little vectors on there, and then using my direction vector to get anywhere on the line. In this case, I'm getting to OP1. So all I have to do now is pretty simple. I'm just going to subtract OP2, the vector from both sides. Okay, so I've proven condition 1.
that look all right? I think we've got doppelganger Megan in here now.
How much?
She's not moving.
I don't know.
I don't either. She's freaking. Oh no.
Okay. I'm the only one that has doppelganger Megan, but at least she talks.
Yay.
Okay.
She's still in perfect time. I can still hear you.
Did you, so did you see the green screen YouTube movie of you and Natalie, Meg?
No.
No. I sent you the link and everything. Okay, so we've proven the first part. So let's see if we can prove the second part. Okay. So we've done this, right? We said, oh yeah, OP1 is equal to OP2 plus SD. So since the two lines are the same, so once again, since those two lines are exactly the same, there's a second point where I just moved along the line from OP1 to some point D. It's going to be equal to a point that is some starting at OP2 and some scalar multiple of D2. So to prove my second condition, I'm going to subtract number 1 from number 2. And hopefully I'll get the one direction vector being a scalar multiple of the second direction vector.
Yep.
I'm going to subtract this. I'm going to subtract this. I'm going to subtract that. So my OP1s subtract out. Wind up with D1 being some scalar multiple of TD2, sorry, of D2. Subtract some scalar multiple of D2, which just simplifies to being go it this way. So here I have my first direction is just a scalar multiple of my second direction vector. Okay. I'm going to share my screen because that's just the generous kind of guy I am.
Sometimes you cheat, and it's the best stuff.
RJ is saying I'm generous to a fault. Oh, geez. It's got the answer in it and everything. I don't want that. How'd I do? I did great. Let's try another. Okay. Find a direction vector for a line that's parallel to that. I'm going to type in the bracket because that's easy. RJ? So we need a line it's going to be a line that's parallel to that, not necessarily coincident.
So, negative 1.
Okay, RJ's picked -1. Meg, if you can talk, what would be the next value in the direction vector? I think RJ's gone for like the lowest common denominator. This is a pretty easy. I wonder if it'll mark us wrong. Okay. What would come next? RJ, you can probably answer this. 4, 3. Yes, judging by this direction vector, I really think that that is parallel, but maybe they'll be disappointed. If they don't uprate us, we what do you know? It's parallel. Give me one that isn't the same direction vector, RJ, this time. Oh, wait! They gave it to us in a slightly different form. Great. Okay. Give me a direction vector parallel to that. Oh, it's very complicated. Okay.
Ten.
10. There's a lot of brackets there.
Yeah, I know.
Yeah, but it's 10.
Negative 10.
-10. And
Negative 10.
-10. Meg, do you agree? Thumbs up if you agree with RJ's choice.
No, it's the right hand button.
Okay. So,
I
okay. So I'm gonna unscreen share because I'm non-generous.
The one that hasn't stopped the screen sharing, so I can still see the question.
RJ can still see the question.
It's fine.
Okay. So this is x equals 5t plus
Okay.
plus 3.
No, plus 5 is the last one, right?
Oh, right. Yeah.
See.
So
One,
this is in parametric form. So in vector form, this would have been 3 plus
S 5.
yeah
And 5.
t and then
Or yeah,
t and then like a 5 here. Okay. And then y is equal to, oh gosh, that's
negative 5 to minus 5.
-5. And so
That would be negative 5. Okay.
and then t would be
Negative 5.
-5. So this is our direction vector. We're just building it out. And we're building it out because we know when we're looking at it in parametric form,
Negative 5 plus 5.
-5t plus 5. So what was the position vector altogether, RJ?
3 negative 5, 5.
3 -5, 5.
And that's another negative 5.
And that's another -5. I don't know why they have such a complicated
The one from Snowy, he's,
So this is that position vector. And this is the direction vector. And RJ went right over the top to find a parallel direction vector, and what did you do?
double.
He just doubled everything, so 10,
Oh, okay.
negative 10.
Isn't it 5?
Yeah, so that direction, like 5, negative 5, negative 5, that would definitely be parallel, but I challenged RJ to go ever more ambitious there. Okay.
Gotcha.
Okay, let's see if we got it right.
Even though I'm more ambitious than that's just better.
Okay, you can't see because I'm not sharing my screen right now, but
Maybe.
we got it right. Okay.
I see a lot of screens in here.
Oh, RJ still sees a blank screen. Okay. Meg, give me one that's parallel to that. Then I can hear you now.
Negative 15.
Whoa, this is even harder than RJ's.
12. Negative 9.
All right. Very carefully said.
Yes.
There we go. Yep. So you just picked a vector that was a scalar multiple of the direction vector. Okay. RJ, I want you to give me 1 point that lies on that line. Oh, you lazy. I see what you're doing. RJ's got the giantest smile on his face right now. He's getting...
Was negative 3, negative 6, 1, all that. Oh, wow. Alright,
Yes, RJ. The position vector, the tip of the position vector
Alright.
is in fact...
So,
no, that's good.
a valid one would also be
That's a good valid one.
negative 1, negative 11, and 6.
And 6. And how did you pick that one?
I just added the direction aspect.
Yes. So you just added the direction vector. What value were you using for the parameter t?
Just one.
So you gave t the value of 1. You found a second point on the line. How did you do? You did amazingly well. Okay. Here we are. Meg, can you give me 1 point that lies on that line?
Negative 5, negative 3.
And 3. Good. Okay. Pick a second point. This time t can't just be 1. Well, I guess t could be 1. That's fine.
Negative 12.
Negative. Oops.
12.
Really?
Wait.
That wouldn't work.
No.
Come up with one. Go ahead, RJ. We can use t equal to 1.
So what is randomly called?
Okay.
So negative 11,
Negative 11,
negative 6,
negative 6. So,
5.
so you just picked a value of t equal to 1. How'd you do? Whoops. You did great. Okay. Take a look, RJ. Which of those points lies on the line? Boy, you have to do a lot of math to get this right, eh?
Yeah.
So is the first one lie in the line? If x is 2, that's negative 2 over negative 4. That's 1/2. Y is 3, that's negative 2 over negative 4, so that's 1/2. If z is negative 4, that's negative 5 over negative 5.
Which is 1.
So that one doesn't work. Does the second one work? It's negative 1/2.
It's the last one.
You say it's the last one. So 0 minus 4 is negative 4, divided by negative 4 is 1. 9 minus 5 is 4. Is positive 4 divided by negative 4. That becomes negative 1.
Yeah.
So it's not the last one.
Third one.
Yeah, it's the second one.
So negative 4 divided by negative 4 is 1. Negative 4 divided by negative 4 is 1. And negative 5, yes. How'd we do? Yay! Okay. So 3, 4, 5, 6 in the exercises. Sound okay? I think the first ones are too easy. For number 6 is interesting to me because basically, if you're given the two direction vectors, you can just use the dot product of the direction vectors to find the angles. Okay? And that's different than the scalar form of the line that we had before. Okay, so you use the dot product, and that's equal to the magnitude times cos theta. What's the direction vector for L1 down here in question number 6?
Or is it?
It's 3, 5, 1. That's right. Okay, these would have been the coordinates of the position vector, and then this would have been this is what you would normally be multiplying by that parameter t. Okay, does that sound all right? Doppelganger Meg?